Hello and welcome everyone. So from this lecture onwards, we'll be having a separate series of lectures on deep learning systems. To just give some introduction of deep learning systems, so we'll rather code these stuff up because whatever we have learned, that was the part of theory. And in order to see how to make computers understand this, how to make computers do such things like train a neural network and what to do, what goes underneath. So specifically, I'll write a target here. You should be able to understand PyTorch. At least at the abstraction level, you'll be able to understand and you can sketch out what the operations that are happening inside. Suppose when you are writing a is equal, suppose you are importing torch and then you are writing a is equal to, suppose torch.tensor or something of this, or torch.tensor and something giving arguments. So you should be able to know or sketch out what might be happening inside. Okay, and we will also try to create something like PyTorch, mini PyTorch, in which we'll write most important capabilities that should be there in order to perform the operations of neural network, in order to make a neural net and train it. Okay, and that will be the focus of these lectures. Okay, now we'll start with differentiation again, and you might be bored to death by hearing these words, so we'll again start with differentiation. So you know that differentiation, like particularly computing the gradient. So when you have to compute these bunch of derivatives, so we call that gradient. So it is a mathematical backbone of these modern machine learning on deep learning algorithms. So what it does is it enables us to optimize these models. So you know all of this stuff. So now we'll again see that where it fits in the framework. Okay, I'll keep on reminding you this stuff so that this somehow gets stuck to your brain and it won't be lost somewhere. So you know that we'll start with data. So we have this data in which we know that it contains information and we want to learn that information somehow. And this is the first step we assume. Second step is we have this model, or which we call the hypothesis class. So we have this hypothesis class. So what is this hypothesis class? So we have family of functions. So we have a family of functions. Let's say h theta of x. So which are parameterized by theta. So it can be a neural network, it can be a machine learning model, it can be any model. So this is called a hypothesis class. A class of functions which we can use, let's suppose, to model something, and we generally call it a model also, like linear regression, neural network. So all of that can be called as a hypothesis class. And once we take one thing out of that, that can be an instance of that hypothesis class. And once we choose a model, so then the third important thing is loss function. Because you have to now quantify how better your model is. Once you choose a model from this hypothesis class, you have to quantify numerically that, okay, I have chosen this model based on these, if it's a parameterized model based on these parameters, how good is this model? So we construct with a loss function. Now, one more important thing in this loss function is, which I can write as fourth step, you have to learn or optimize. So generally we wrote learning method, and then today here we'll name it as optimization method. Optimization of method or optimization function. So what is this basically? So here in loss function we have seen binary cross entropy, we have seen a lot of other functions as well. So in the optimization methods, so you have to iteratively update these parameters. It's a parametric model, so you have to iteratively update these parameters. So here is the thing, here is the most important point where we use these derivatives. So that's where these derivatives fit in the bigger picture. So you should know this, like why are we focusing so much on calculus? Because all of this data, we have hypothesis class, we have this loss functions, and in order to learn a model, you will have to optimize something. You'll have to have optimization methods, and in those optimization methods, you will use these derivatives. Okay, and now we will see how to compute these derivatives numerically. Okay, how to compute the derivative without the computationally. So we'll see what are the computational methods to perform this. Computational methods to calculate derivatives. So these lectures will be a little bit code heavy than theory heavy. So we'll write a lot of code to understand this stuff. Okay, and because I assume that you have understood the theory that we have discussed in the previous lectures. Okay, let's start again with the code. So okay, we'll have a function and we can write that function, and after that I'll tell you what to do with that function. Okay, so I think you also can visibly see the things I write here. And you know what is the derivative. So if you see what a derivative is, so you will have a function, let's suppose something of this f of x, and if you want to take a derivative of this, you have an easiest method. You can take, suppose, f of x plus some small value h minus f of x divided by the small value h. Okay, and that's why you write this limit h goes to, let's suppose, 0. So this is how you compute the derivative. Okay, so if I take this, if I take the same thing and convert this into the code, okay, let me just show you that thing and we'll get started. So we'll initially import the important libraries. so that we can easily plot stuff. And do let me know that if the code is visible. I think it is visible. Okay, so this is what I have done. I think it's just good. So then the first thing is I did these imports. Now if I write a function, suppose I write a quadratic function. If I write a quadratic function, say I'll name it as definition quadratic, and I'll write all of these this code will be written in Python. So I'll write this function. So what is this function? Now it will return something. Okay, it has written a function. I'll copy paste the code in order to save the time, and I'll explain you parallel what I'm doing. Suppose we have this quadratic function. So let's suppose we can change these values to 5x. Let's suppose instead of this 4x, we can write some 7x or something of that sort. So you have this quadratic function. Okay, and now if you want to compute a derivative of these things or something. So first let's see how this function looks like. So we can say x values, and we can compute y values. Suppose we have some x value that is equal to this. Say we have some x value is equal to this, and if we want to compute the y value corresponding to this, or function value corresponding to this, you easily know what can we do. We'll write f value, this quadratic function, and give this value. If we print it, you can easily see that this value will be printed over here. Okay, so this is 29.0. So now if we want to see the whole graph of this, so how do we plot the graph? So I'll take a range of x values, and I'll apply this function on that range of x values in order to compute with y values, and then I'll use matplotlib to come up with the graph. So first thing is, let's come up with the generate x values. Okay, how to come with x values? Pretty easy. So you know that we write this x range function is npa range. It will go from let's suppose -5 to 5 with this step size of 0.25, something of this, and then we'll compute this y range. So how to compute the y range? So we'll just apply this quadratic function on the x range. So if I write that, so that will be y range quadratic function x range. So now I have x values and I have corresponding y values. I can print both of these values. If I show you, so I can, let's suppose, print, you have seen this y range. So you know, oops, have we defined numpy? This cell was not executed. So now you see this. So you have x range and you have this y range, and these are the values corresponding to that. And now you know how to plot the function. If I have to plot a function, so I'll just paste the code of plotting. So here you can see this. So this is the plotting code. So what is this? You can see plot out figure. So I'm making this, and then I'm telling you plot. This is the x range and this is y range, and give the label corresponding to this. And I have changed this function, so you can accordingly change the code. And this is how these lines should look. And this is you also write a scatter plot, and then I'll show you this code. Suppose. So if you see, this is the point at which we wanted the value, the 2.5 point. Okay, so I'll just make it a little bit smaller so that the whole graph is visible. So if you see this over here, so this is the visualization of this quadratic function. Okay, and now what is the derivative over here? So if you want to compute derivative, I know you people know that what derivative is. So derivative basically means the rate of change. We have to see the rate of change. So in this, if you see clearly, this red point at say x is equal to 3 or x is equal to 2.5, whatever the value was. So this shows us that at f is equal to 3, what is the value? So the value, let's suppose over here, if it is this 3x square minus 4x plus 5, at x is equal to 3, I think this will be 30. So you can see that value. And now we'll have to compute the derivative of this. How to compute derivative? You know the formula. The computer, in order to compute derivative, you'll have this function f of x, and you will perturb it a bit. You will add some value h to it, because you want to see the rate of change and instantaneous rate of change. And then you will say this value f of x, and then you will divide by h. This is what we will do. Okay, let me write that in the code as well. Okay, so how I can do that? If I have to do this called numerical derivative, so I'll write the code for numerical derivative. So suppose numerical derivative, I'll name a function definition of numerical derivative. Okay, this is numerical derivative f x h, and then I will return the same thing that I wrote mathematically. Okay, so I'll return this. So I'll say f of x plus h minus f of x divided by h. So this will give me the numerical derivative. Suppose if I write h is equal to this, so I will write h is equal to 0.001, and that I will compute a derivative at a particular point. And we have defined x point at the top, the value of x point, if you see over here. So this is the point, x point is 3. So we want to compute derivative at a particular point. Okay, usually the rate of change is actually to be computed via 2 points. So we should have 2 points in order to compute the rate of change. But that is a specialty of derivative. You have to compute instantaneous rate of change, and this rate of change will be at a particular point. So you have this point, I'll compute this derivative approximation. You take this derivative and you give this a function. So you are giving this as a function, and then on this function you are applying this argument and subtracting the f of fx and then dividing by h. So this is my f of x. So f of x is the function. So, and after that, what I'm trying to do is I'm trying to give it a point, and I'm trying to nudge the value. So I have x point, and I'm trying to nudge it a bit, and then I want to see what is the change, and I want to print the derivative. So now if you see this, So if many of you people will know, so let's suppose if I write this function again, so the function over here is this. So this is the function. So if I copy this function and I'll paste this function over here so as to have this in the view. Okay, this is my function, suppose. Okay, you know, if you take derivative of this with respect to x, and you know it's a quadratic function, it will turn to linear. The answer should be 5x. So and all of this, so let's suppose the 5x minus 7. So if you take derivative of this directly by using symbolic derivative representation, and you can use that, you can see that taking derivative with respect to x, you will get 5x minus 7 will be the derivative. And if I have to compute that value at point 3.0 now, this is 5x minus 7. So 5 multiplied by this x point now. So x point is 3. So 5 into 3 is 15. 15 minus 7 is 8. So the value should be 8. So now we should get the same value by this. Okay, by the definition of derivatives. Okay, so if I have to print now these points, so what I will do is I'll paste these lines of code over here. So this is, oops. So if I just paste this, so the numerical approximation says, so this is the numerical approximation and this is the actual derivative. So actual derivative should be 5x. So this is 10 rather, I think I have made the wrong calculation. So 5x square means 10x. So 10x minus 7. Okay, 10x minus 7 in this case will be 10 into 3 means 30. 30 minus 7 is 21. So this will be 21. So this value should be 21 and the approximate value should also give us 21. So if I just write it, I think 23. Some calculations here and there. So this is 10. This is point. Can you take the calculation? So is it right? 3.0, this is 30. 30 minus 7. Yes, 23. Yes, and 30 minus 7 is 23. Yes. So because I'm thinking a lot at the same time when I'm speaking this, so I'll have calculation mistakes will be there. So if you see, this is right. So I did this with the numerical derivative by applying the formula, and the second thing is I did it with the actual derivative by using symbolic representation. So as you can clearly see that this function was 5x squared, so the derivative will be 10x minus 7. So that's what we have written over here. The derivative is 10x minus 7, and that is what we have over. And now if you see, this is an approximate value. There is some value here and there, but you can see this and these values are pretty comparable. So this is how you can compute the derivative. Okay. And now usually you will not use this method to compute derivative. As I said in the previous class as well, you won't use the symbolic representation. So you will use what is called autograd or automatic differentiation. So we'll later on see that also, but here usually we use these methods to check. So these methods are used to check the derivative, because these autograd derivatives computing that it's a bit hectic and it involves a lot of symbols and a lot of computations. So sometimes you're not sure is the calculation right or wrong. That's why I'm showing you to write these things as well. Why? Because once you code these things up of autograd or you code these things, and you will have to have a comparison method. So what you should do is you will compute that thing with this, with let's suppose numerical derivatives, and once you apply the autograd, automatic differentiation, and then you should be able to see, okay, the answer is quite near, that means my answer is correct. Okay, let's do a little bit better example than just a quadratic function. We'll take some linear combination, because you know in neural networks what do? We take some linear combination or affine transformation that we call. Let's take three values a, b and c, and I can write a multiplied by b plus c, something of this sort. Come up with a function of this sort. So we have function definition linear combination, and it will return a multiplied by b plus c. So if I return this value, return a into b plus c. So now I can give some initial values to a naught, b naught, c naught. So I want to create a function of this now. So these are the initial values. A naught, b naught, c naught is mine, 2.0, 3.0 and 10. And if I have to have d naught now, so this is what we do in the neural networks. We will have these weights and bias instead of this. So we'll have d naught now. That is the linear combination of all of these values. Okay, I can print the initial value of all of these things. So I can say initial value of this. So you can clearly see initial value of d, 2.0, 3.0 and 10.0. This is 4.0. Once you compute all of this linear combination, so this d naught is equal to this. Okay, so d of these values is equal to 4.0. Okay, now if I have to again compute the numerical partial derivatives, in this case we'll not compute the whole derivative now. We'll compute the partial derivative, and you know what partial derivative is. So in that, other things will be kept constant, and what will you do? You will just with respect to whatever you are taking the derivative with respect to what, and you will keep that term as variable, and rest of the things will be constant. Okay, let me also write a definition of that. So we'll call that numerical partial derivative. So numerical partial derivative will be written like this, and then what we'll do is we'll say perturbed values, because we'll have a lot of these values now. So we can say we'll create a perturbed list of inputs. So if you see, we're taking this function as an input, okay, and then we're taking variable index, and then we are taking these variable index. Basically means which among these lists the values is a variable, and rest will treat as constants. And the first thing over here is we'll create a perturbed input. So perturbed input is equal, let's suppose list of the inputs, okay, and perturbed inputs will just take that particular will index this whole list, and we'll just perturb that value, that particular value, okay, and then we'll say the perturbed inputs is equal perturbed inputs. Basically we'll make a tuple out of it, okay, and after this we'll return this again, the same thing, okay. We'll return this f of, so because we'll be given a function and we'll have these perturbed inputs minus the actual inputs that we had divided by h. So we do the same thing, but rest here because we had a lot of inputs. Again, to show you this in the picture or writing, because I can now consider mathematics as picture. So if you have, let's suppose, some derivative, you have a multiplied by b plus c, okay, and if you have to take derivative of this with respect to a, partial derivative, okay, so what you will do is you will consider this to be a variable and these to be constant, but you know this. Now you have these values a, b and c. This will be a suppose a list of values. So you will take this as input and you will take function and you will take the index. Let's suppose here you have index this at index 0 index. So this is what we will perturb and rest will keep as constants. And that's what I'm writing over here. If you see, this is what I'm writing. I'm saying perturbed inputs is list of inputs. So what are inputs I'm getting? Okay, and this is with respect to what are you differentiating? Okay, and once you get these perturbed inputs, and on that list, basically you will be forming a list of this sort. Say list is this is a, b and c, and you just want to perturb this value a. So how will you perturb this? Because you have this variable index. So you have the index on at which you want to perturb. So you will just increment this value. So that's what I'm doing for perturbed inputs. Variable int a plus is equal to h. So I'm just incrementing this value by this value h. And what I'm after that doing this perturbed inputs. Now I'm saying this is a tuple of all these inputs. Again, make a tuple of this. Okay, so make a tuple of this, and then I'm saying return this. So apply this function f on the perturbed inputs. Okay, and then minus f of these inputs. And if you see, I have written star over here. Why this star? Because it'll unpack these arguments. Okay, if you haven't learned enough Python to understand this. So perturbed input, it will be a list of these things and it has to unpack this function. It will have to unpack these values. Okay, so it will unpack these values and apply this function onto that, and then I have written divide by h. Now okay, let's compute this partial derivative. Suppose we have this again the same thing. We have h is equal to 0.001. Okay, and now we'll compute partial derivative with respect to a, with b and c. So let me do that in one shot. So this is partial derivative. So you will take this numerical derivative, linear combination function, because this is the function that you had, and you want to say index 0, basically partial derivative with respect to a, and then partial derivative with b. So you'll just change the index a1 and then you change the index over here. So if I see this, so you can compute the partial derivative with respect to a, with respect to b and c over here, and these are the values, exact values. And you know why are you computing it, and you are giving that particular value also over here. I hope this is clear. Any questions still here? So if you understood this, let's move forward then. Okay, and you can also plot these partial derivatives if you want to see these partial derivatives, because you know again this will be linear. So we can fix, let's suppose, something, and we can fix b and c and vary, let's suppose let's suppose we'll take this a and we'll make it vary from say -5 to 5, and we can show you the graphs as well. Okay, let me show you that as well if I write that code. So what I was trying to do over here, we are fixing b is equal to -3 and c is equal to 10, and then we are varying a from -5 to 5 because we want to have different a values, and then we are taking this, and you can have these partial derivative plots, something of this sort. So you will see this. Okay, so this is partial derivative of d with respect to a. So this is -3 roughly. So partial derivative of b with respect to partial derivative of d with respect to b is roughly 2, and partial derivative of d with respect to c is 1. And now we are seeing, given that a is equal to 2, b is equal to -3, and you are taking this c as variable. Okay, I hope that this is clear for everyone. So now if you have understood this, let's move on. So in order to do this now, the first thing is we'll have neural networks. So in that neural networks, if you understood that, so what we should do is, let me just, okay, so in these we'll have these different expressions. So we'll have variation bias, you'll have w x plus bias, okay, something of this sort, and then you'll apply some function onto this. Okay, so each of this value, if you take, suppose we'll take the expression, the small expression, we have a multiplied by b plus c, something of this sort. So now we have learned about computation graphs. So we saw that we have a, okay, and then once you, let's suppose, take a and you multiply this, you have b, you multiply this, and you will get some ab. Okay, and then you add some c to this. So you'll add some c to this. Suppose you'll add c to this, and then you will get an expression d, something of this sort, and all of these will be nodes in that computational graph. Okay, and each of this, if this is a weight or a bias, so this will be having corresponding, like let's suppose for this particular thing, so it will be having gradient. So if we have to compute gradient with respect to this, so we'll have a loss function at the end. So here we'll have loss function. So loss function's gradient will be computed with respect to this. Let's suppose AB. What is the derivative of loss function with respect to this node AB? And you should know how did this AB came into the picture. So because we had this A and B and we multiply them together and then we got AB. So you have to have these things in the mind. So if you now have to construct a thing like that, where you should store gradients, you should store what operations were there, and let's suppose which children are there, something of this sort. We'll have to come up with our own data structure. So now you saw that we have these nodes, and now for these nodes we should have some user defined data structure. User defined data structure. That's why we'll use classes. Okay, so we'll have to have these parameters, because you know that each of this can be considered as parameter. This is a weight or a bias, so it should have gradient corresponding to that. It should also have which operation actually was done in order to get this, and what are the children nodes, or what are the nodes which resulted in this. Okay, so let's suppose if you have this A and it has two nodes, it has some C and D. So you know this A was the causation of this C and D. Similarly, in this case, in this particular case, this AB, we got it from A and B. The A and B can be called as children of AB. And then we had this operation star over here. So we said, or multiplication. The operation multiplication once performed on this A and B gave us the result AB. So we have to come up with our own data structure, and we'll here use classes. Okay, you'll use object-oriented design. So we'll first come up with the classes. Okay, we'll write a class which is known as parameters, because I now want to first create those weights and biases. Okay, after that I'll create a whole network out of these things. I'll put them layer by layer, and then I'll apply forward pass, I'll apply backward pass. We have to learn all of that stuff. Okay, let me start with that. Now, so far what we have done is we just learned about derivatives and where they fit in. So I told you there is a method which is called as numerical derivative method, and in that you basically use the definition of derivative and you get the approximate answers. Okay, and in order, there is one more method that people generally use. I should also tell you that is way more accurate than the first order derivative. So even when you use this method, and you generally use this f of x plus h minus f of x, so it gives you some error. Okay, so in order to reduce the error, there is a method, this is which is called as two difference method, I suppose. So we have difference method, and this method basically f of x plus h minus f of x divided by h. This is called difference method. So now in two difference method, what you generally do is, so you will take f of say x plus so this will be some h value, and then f of x minus h, and then you divide it by 2h. So this thing is called as two difference method, and this is more this gives you more accurate value. So this is more accurate than this. So generally, in order to check, so you'll use this method. So if I write this in terms of say these theta vectors, so if you have this f of theta is your function, and you want to take the derivative with respect to some theta I, so because you will have a lot of thetas, so what you will do is, so you write it like this. So you write f of theta plus epsilon, or maybe that h is the small value, and I'll write ei. So what is this ei? So this ei is the one hot vector, so it is 0 0 0, and just on ith value it is 1, rest it's again 0 0 0. So because you have all these, you have a vector of this, so you take all these thetas and you just want to put up one value. That's what we did in the code right now. And then this is minus f of theta divided by epsilon. Okay, here you know that limit epsilon tends to 0, something of this sort. Again, similarly, if you have to use two difference method, okay, which reduces error, so there you will say f of theta divided by, say we are doing it with respect to theta I, as in this case. So we'll now take two differences, limit of epsilon goes to 0, f of, and in this case we'll take theta plus this epsilon ei minus f of theta minus epsilon ei, epsilon ei divided by, this is 2 epsilon. Okay, so this is the two difference method which is more accurate. So this gives more accurate results. Okay, and y part is left to you people, and because you know Taylor's series, so you should be able to tell me why is this so. Okay, I'll just leave this, and because we'll be mostly probably either using this or this for the checking purpose, because as I told you, this is not the optimal way to do it in computation, but it will directly give you approximate answers and you can just check your value. So how do we generally do it? So what we basically do is, so we have something called as numerical gradient checking. So in that, what we try to do is, so we'll have some delta t, so we'll take some random value delta, and if you have to compute this, okay, so you will use the definition epsilon of, so you'll put up these values a little bit, and then you'll use, let's say if you use two difference method, divided by, so 2 epsilon. So you'll use this. So what you basically try to do is you'll compute this by autograd. Okay, on the left hand side, when you want to compute derivative, you'll use some method. Okay, so on this right hand side, you'll use this numerical differentiation method, and you will choose this delta coordinate, and you will compare the value. Are they accurate? Are they do both sides agree? So you will use this to check the gradient. So this is called gradient checking. So gradient checking. So why do we need to check the gradient? You know why we need to check, because we will be performing a lot of back propagation and we'll have to check the gradients all the time. Okay, with this this was just a cover up. This was just a revision of what we covered so far. So we're discussing about, we have to come up with this parameter. So we have to have parameter in which we should have gradient, and we should have operations correspond what operation led to this, and we should have what are the children it has. Okay, so all of these things should be kept in some data structure. So as I said, because we don't have the data structure but we can directly keep it, so we'll make a class out of this. So once we make class, at least it should hold gradient, operation, children, and we'll see if it holds some other things, and we'll keep on adding the functionalities to this. So this is similar to what we have in PyTorch tensor. So tensor, in that tensor you have, let's suppose it holds a value. Okay, more important thing is it should also hold a value. Okay, by value I mean, let's suppose this a can be 2.0. It should have some value. Weight will be having a value. Bias will be having a particular value, and bias will be having a gradient with respect to the loss function. It will have what operations led towards this. Okay, and it should have the children's, basically what led to this, and we will create a class now. Okay. Okay, after understanding all this background, and now we'll go to code, and this code will be used in the library. So this is the primary thing that you should write, because I expect from you people is that once I write this code, and many of you people will clean up the code, and what they'll do is they'll have separate files for all of these things, and then they'll make a mini PyTorch thing, and we'll later on name it. Okay, now let's go to the code again. So I hope the code is visible now. Okay, let's call a class parameters. Okay, we'll make a class parameters, and first I'll import some things from a module called as typing, because it will make my life easier. So I'll import, let's suppose I set tuple, and I'll also import math if I need it. I might be needing it. So the first thing that I'll do is I'll create a class parameter. Okay, let me call that class params, and this will be my weights and biases. So if you see PyTorch will have this as named tensor. So we'll name it as here as parameters. The first thing is I'll write this constructor or the initialization. So what I'll do is I'll write def initialization. Let me write these things. So def initialization, and I'll start with self. So you people will be well versed with all of this syntax. If you have problems, please let me know. The first things is we'll take data, okay, or the value, which we call as value. So that value generally is a float value. We'll take float values. Okay, and the second thing, as I said, okay, let's first make this, and then we'll later on. So we'll initialize this value. I'll say self. Okay, and I'll say self.data is equal data. Okay, I'm initializing the data, and now I can create a class. Okay, I also need to define operations, but first thing is I should have these things. So if I, let's suppose now construct a class, I'll say my a is equal to params. So if I construct some value, params of say 2.0. So if I, okay, this runs correctly. So this is called instantiating a class, or we are making an object out of this. So you have a, so now this gives value this. So you know that we have some dunder methods. So these are called as magic methods or dunder methods in Python. Okay, because I have not taught you Python object-oriented programming. So whatever clarifications I'll need, please ask me, and I'll give the clarifications, and whatever I feel is needed, I'll do that. So in order to print these values, so what I'll do, we have a special method which is called as wrapper method. Okay, what I'll do is, so this is the method. So we have method wrapper. So if you don't want this ugly looking thing, so you basically want this value actually. So you will from your own side, you will define this wrapper method. This actually is defined, so you'll basically override this method. And what you can do is you will just return one thing. So you will return parameters of data. So let me, and then we'll keep on. Okay, so is this right? Okay, I'm returning this. So if I return this now, so you will see that it is now showing params of data. So I will close this brace over here. So look, if you see tensor, so when you click on print tensor, something of this will happen. So if I now write print of a, so you can see this. So this wrapper method is actually giving you the access to that, to the values in that. So now I am saying, okay, give me this value in this format. So that's why I'm using this wrapper method. Now let's suppose if I have other value b, so I'll say b is equal again params, okay, of say 3.0, and now I have this value b. Okay, I have value a and I have value b. Now if I want to add these two things together, suppose I want to add, I want to say a plus b. So I have this a plus b. So if you see, this is an unsupported operation because it expected something. I have not, this operation is not supported in this class. It's not supported. So what I'll again use render methods in Python. So actually when you do this a plus b, internally what Python actually does is, so if you, even without this class, I'll say 1 plus 2. In this case, I'll say x is equal to 1. Okay, say y is equal to 2. Okay, when I'm saying x plus y, so x plus y, this is saying 3. So you know actually internally what is happening? Internally this thing is happening. So I can say x dot add, okay, and then this y. So this is what is internally happening in Python. X dot add y. So if I now again do the same thing, I'll get the same answer. There will be no change. So basically you know that each thing in Python is an object. So you see this x is an object, this y is an object, and this add is the method. So now I am creating this class. I should be able to add these two things together. So how to add these two things together? I'll again define my method, that's add. So what I'll do is I'll say definition add, okay, because again this is the magic method, okay, or render method. So now I'll say self to call it, and then I'll say other. Other basically is the other method. So other. So what should be other? So other should be again a very instance of param. So this param is basically this. I want this params. Okay, this basically I want other value to be also. So if I am having a, I'm having b, so I should be able to add them. Okay, once I have these two things, what will I do is, so I will add these two things together. So how I can add is, I'll take the value of a and value of b. I'll try to add them. So I'll say add, or I'll say return out. So what I'm trying to do, if you see out, I'm saying take the self of data. Okay, self of data basically means, so it will take this data and add this other of data. Okay, so let me just remove all the other things because this is the code that I don't want right now. So I just want two things. I want self of data plus other of data, and then I just want to return that. So now I should be able to perform the addition. So if I do a plus b, so you should be able to see a plus b params is data. So I can even say this is equal to c. Okay, so I can now print c also. So if I show you c, so now you should be able to see this. Okay, so I have this a is equal params of this, b is equal params of this, c is. Now I also want a label. Okay, one more thing that I forgot while showing you the structure that we wanted to make. So I also want a label. So what I can do is I can say label over here also, comma label. Okay, so label basically means I should also name the node. So if I have weight or a bias, weight 1, weight 2, weight 3, something of that sort. So label will be one more parameter. So it will be of type string. I don't want to do type checking, leave it. So I'll say self dot, and then I should have label that should be equal to label. Okay, so when I'm doing this, so a is equal params of this. So this is optional. So let me make it optional. Okay, so let's take some default value of this sort. Label is equal to some default value. So let me just check if it works. Yes. So what I can do is I can say a, this is comma label is given is a. So label given is a, and for this b, label given is b, and for this c, let's suppose c is equal to this, and I can say c dot label. Label is equal to c is equal to c. I'm giving it label also. And now I also want to print that in the wrapper method. And I don't just want to print the data. I also want to print the label. I'll write comma label is equal to self dot label. Okay, and I think this should work. So if you see this now, if I print the c, okay, you can see this params data is 5.0 and the label is c. So I am also holding its label because I want to make the whole computational graph. So the first thing that you saw is I am initializing everything in the constructor, and then I am writing this wrapper method in order when I call the print something, so it will be calling this, and if I am calling that particular object, and I am adding this method over here. Okay, one more thing that I should have is I also should hold operations, because this c was the result of operations. So I will also have operations. Any questions in here so far? Okay, now you saw that we again added this label over here, and we have added one more function, that is add. And I also want to add children. Okay, so let's call this children. So we'll say, because we have to see, okay, if we add these two things, if we perform some operation, or before children, we'll also have to have operation. So you have this add, so I will also have an operation over here, so comma operation. Okay, by default, this should be compulsory rather. Okay, let's make this compulsory if we are making this. So we'll say If we have to make it compulsory, we'll say operation is a string and we'll give it empty string by default. If there is no operation, that is by default. And if we're adding these things, so here, so this thing should be taken. So this in add, so this will automatically take add. So this will say operation is equal to add, comma, operation is equal to plus. Okay, that's what I want to do. Give me a second. I did some mess up over here. Okay, in this I'll say self dot operation is equal to operation. Okay, so what will happen now is, now if you call this params, so if you don't give any operation, so basically it will just give this data and label, and if you don't even give label, so I'm making these as optional because I'm giving these default values. So if you now perform some operation, so you're saying C is equal to A plus B. So if this operation is called, now automatically, now the C is a result of A plus B, so this operation will be stored. Okay, so if I again run this, okay, let me run this. Let me see if there is no error. So if I now see C dot operation, so what is the operation that caused it? So you can see some problem is there. Let me check the code. So in order to see this, so you saw, so what we did is we defined one more thing, that's operation over here, and I said operation is equal to plus in this addition. So if I run this now, okay, so you can clearly see that C dot operation is now plus because this was an output. If I now let's say minus, this is not again defined. So how to define this? So I'll copy whole of this code and I'll just paste this. Oops. So I'll say subtraction. Okay, this again will be a dunder method. So I'll say subtraction over here. This is my subtraction. So I'm saying self other. So data, take this data and just subtract it and give subtraction. So I'm saying A is equal to param dot this, B is equal to this, and I'm also giving this and C dot operation. So or even if I print this, I can also print operation over here, but I don't want to print operations all the time. I just want to print the data and the label. So now this C dot op, if you see, this is minus. So what we did is over here, so in the initialize or constructor, we defined this operation and we are setting it in the parameters in these operations and are performing addition or subtraction, and we are giving these operations. And now one more thing that we want, I said we have value, and let's suppose we have these parameters. Parameter will have this data or value, and it will have label. What is the label correspond? It will have operation, what operation calls it. By default, it will be empty string if this was a leaf node, or if it was intermediate, it will be caused by some operation. So that operation is kept over here. And one more thing that we have to keep is the children. So we'll see, okay, what are the two values, or what are the values that we took in order to reach there. So what we'll do is we'll take children. We'll again define the constructor. So let me define it over here, comma children. Okay, and this children by default, let's take it set, or we can take it a tuple also. Let's suppose we'll take a tuple of these parameters, or even we can say set, and it depends. We'll see. For the efficiency, we'll later on make it efficient. So for now, I'm taking it as tuple. So this children will be a tuple of these parameter values. So let's suppose if you created this add, so because add, once we did it, it should have also children. So what are the children? Children is self and other children's. Okay, so what I'll do is I'll say data, self dot data is this, and other data of this, and I am giving this as params, and comma, instead of children's, I'll give it a tuple like this sort. And what is the this is self, comma other. Okay, same thing over here, same thing for the subtraction. So same thing for subtraction. So if I take this, please let me know if you have questions. I'm thinking a lot of stuff in the meantime, so I can make mistakes also, but do let me know if you have questions as well. So what I have done so far now is, so I am also giving this children's as in the constructor, so that whatever operation I am doing, so I am giving the operation corresponding to that and the children. So if I now see, if I run this first, let me run this. So operation is mine. So if I now again say C dot children, okay, now you can see that there is some error. So is this right? So if you if you see this is how I have named it. So now the issue here was I have not initialized it over. I should also initialize these. So once I give these values, I should initialize the values. So children, so I'm initializing it over here. So if I now run it, it should be able to give me. Now if you see params data 2, its label is nothing, and the label is, I should I give labels correspond to this, because if you see this, this is giving me the data of this and that. So I should also give I should get basically this value. What is the label correspond to this? So it is giving me, say if I subtracted this, I'm giving self dot data and self and other. So I can also give corresponding label. By the way, but it's good that we at least got so far. So far what we have done is I think most of the things are here, and we need one more thing, that is grad. Okay, gradient. We'll say we'll need one more thing, that is the gradient. So we'll define it over here, grad. To make not make again the same mistake, we'll initialize it first. Self dot grad, okay, is equal to grad. Okay, and we'll have all these gradients over here, and we'll have to define for these things. We'll have to define gradient, and we'll have by default it will take value 0. Okay, and we'll have to see how to define the gradients, by the way. Okay, and all of these will be having related gradients. So if I now say c dot grad, okay, c dot grad is equal to 0 because it's taking the default value. So far what we have done is we have made a data structure of our own. So in that we had it takes data, it takes children, basically means what are the children that are output of this. So by default it will take but if this is just a value, let's suppose this a value, it will be a leaf node, and then you have this grad basically will store the gradient with respect to the loss function, and we have label. So label will be what would we name that node, or what will be name weight or bias, and then operation, what was the operation that caused it. So these are things we have defined, and now we will define more methods. So we have defined this add, we have defined subtraction, so we will also define, suppose, some other methods. Let's suppose multiplication. Okay, definition. So we'll say we have actually R multiplication. Okay, and we'll keep on defining such functions, and it will take self and other. Okay, let me say pass. So I'll say to do over here. So I'll write this is my to do, everything to do. Any questions still here? Any questions? So if you have any questions, I'll take some questions here. Again, looking at this, if you see, so we have this params over here. So we have data, we have children, we have gradient, we have label, and we have operation. And what we'll do now is, so let's suppose have this a, b, and c. So a is my parameter, for example, a weight, and then we have bias, and then we can have a constant. Okay, so all of these things, let's suppose consider them for now as leaf nodes, because a and b and c, and let's suppose d will be the output of this. So if I print these, so I have one argument missing. So what is that argument? So that is, I think, children. So this is a. So what is the missing argument position? Or children is missing. Okay, that's why I should be very careful while performing this. So children over here also, keep it as set, don't keep it this. Oops, let's keep it like this, so as to keep it empty by default. Okay, now if you see this, so this is leaf nodes. So I have created these leaf nodes. A is equal to 2.0, label is a, parameter is this. And now if I, let's suppose, do something, if I create multiplication, or if I do this, so should I create multiplication? Okay, I think we need multiplication. So what we'll do is we'll create multiplication, because we need a multiplied by b plus c. We have plus, we don't have multiplication. Let's do this definition of multiplication. I want to use RMUL. We have different RMUL and LMUL, so I'll tell you what these are. So right now we'll just use this multiplication, and then we'll use self and other. Self is the object that we are taking, and other is the other operation. And then what will I do is I'll just output params, and I'll multiply these two things. So I'll say output is params of seller data, and multiply with other of data, and then the self and other, this is these are my children, and this operation is equal to this. So operation is this. So if I now run it again, I think it works good. So now I will do one thing. So I will perform this. So I'll say d is equal to a multiplied by b. So I'll say something of this sort. So we have d, that is a multiplied by b, and then I'll say e is equal to d plus c. So basically this is d plus c, that's a multiplied by b plus c. Okay, if I say f is equal to e minus a, so basically I'm telling you this, so you people can easily understand this. So I'm starting with d, I'm saying take a multiply with b. So then I'm taking this d, I'm saying e is equal to d plus c. So d plus c is a plus b into b plus c. So if I just want one more thing, so I'll say maybe I can just stop it over here, but anyway, I'll take f is equal to e minus a. So take this whole e, that is a plus b plus c, a multiplied by b plus c, and then minus this a. So this is my f. Okay, at the end we have this function. So now if we have to print these things, so what I can do is, so I will print all of these values. So after these operations, okay, I do have subtraction. Yes, I do have subtraction. Okay, if you see now this, so print d. Initially I had a into b, so that is params minus 6.0. You can check it. 2 into 3 is minus 6.0, and I still have issues with labels, so that we'll fix, because while performing these operations, these labels are not getting set somehow. So we'll have to see this. Params and label is equal to self dot label. I should also pass the label over here for these. Let me do it. Let me do it for now. At least this is working. So after operation, we have this a multiplied b is this, e is this. So this is, now I have to create a graph after this. Okay, so at least I have at least if I now want to make something of this sort, if I now want to do w into x plus b, something of this, I can have w, I can have bias, I can have some x, I should be able to perform this. Okay, so I can have labels over here. So when I'm doing d, so what I can do is I can say d dot, say over here I can say d dot label is equal to d, because I'm not setting it there. So if you now see this label d is coming over here, I can separately set the labels, and then I can see e dot label is equal to e, and I can say f dot label is equal to f. I think now this is good enough. Okay, so you have a, b and c, and then you perform some operations, and now I want to create a computation graph. Now let's make the computation graph. What I mean by that is, so now you have this a, you have this, let's suppose b, and you have this c, say something of this sort. So you will perform some addition or multiplication to get ab, and for this you'll perform some addition to get, let's suppose a, b plus c, or let's consider this as loss function, and I want this to happen in such a way so I can visualize. So I'll use a library called as GraphViz. Okay, so in that I'll have to use topological sort and stuff like that. So I'll first explain you what I'm going to do. Okay, and then you can ask me questions if you don't understand. Let me clean this up. Okay, the first step is like you have this root node. Now you'll get hang of this. Okay, parallelly I'll keep on writing the code that I want. Okay, so we'll build a trace of nodes. First we'll have to have our set of nodes and edges. So we should have our nodes and edges. So but you know, in the graph we have nodes. So if you have this a and if you have this b, these are nodes, and if we add them, so and we get some other nodes, say ab, so these are my edges, this is my edge, this is my edge, and this is my edge over here, or rather here if you just make two edges, so and this is plus is an operation which calls this, these are my nodes. So in a graph I first want to collect these nodes and edges. That is my first job. Okay, this is called as tracing the graph. So if you have to trace the graph, okay, and you have to have all these, and all of these nodes will be params. Okay, and these edges will be directed edges. It goes from a to, let's suppose ab, or b goes from b to ab, and then also have to draw, and there's a draw function in GraphViz. So I won't be telling you the documentation of graph. You can look that up. So but that's what I want. I will form the trace. By the help of trace I'll get these nodes and edges, and then I'll construct a graph of this sort. Let me write the code. Let me show you the code. And what we'll basically do, we'll try to give it a root node. So if we have a root node, so if I have something of this sort, I have this a, b, and it was product, let's suppose it gave me c, and then c was multiplied with something d, it gave me some e, and this e was given some level f, and we gave it loss function. So we'll give it this L, basically the root node, and it will construct a graph like this, and it will help me visualize. Let me write that code now. So the first thing is we'll add graph trace. Okay, so in the graph trace, so I will again import some standard imports first. Okay, so this, if you see, though I'm importing these, so GraphViz has something called as diagraph. So diagraph will let you have these nodes and edges. Okay, so from this typing I am importing the standard stuff. The first thing that I'll make is graph trace. So I'll make a class, so that's named as graph trace. So what will it do is it will be a named tuple which will hold the result of trace. So that's what this will be holding. It will be holding nodes and the edges. That's what I'm saying. It will be holding a node, and I have created a set of parameters, and then it will be having edges. Edges will be a tuple from wire to wire. So that's why you see a tuple of parameters. So it will hold, let's suppose a comma b. So if you have a graph like this, you have a and b. So now this nodes over here, if you see the nodes will be given parameters a and b. So these will be in the nodes. This will be a set of nodes. And now this edges. So edges over here, let's suppose you have c. So this will be c also. Now edges are a comma c and b comma c. So these are edges over here. So that is what this will hold. So this graph trace will hold these two things. So the attribute it will be a named tuple holding the result of the trace of the computational hook graph. Okay, so nodes will be a set, and this edge also will be a set. So this will be unique. It will just contain those parameters, these a's, b's, and c's, or weights and biases, and edges will be, this will be a set of these two things. So it will have something of this sort, a comma b as I showed you, and then b comma c, something of this, dot. Okay, so this is the first thing that I have done. So I have done this graph trace, and then I'll actually do the trace. Okay, and it should give me output as a graph trace. So what I'll do is I'll say I'm creating a function definition which will, as I said, we'll trace it from the root. So we'll say we have root, and then we'll take these parameters. Okay, so we'll try to build it. Okay, and nodes and set. Initially we'll have these nodes and edges as something of, they will have empty, no sets. This is nodes and this is edges, nothing is in there so far. Now once we go to root, and we'll perform a depth first search, and we'll keep on adding nodes and edges over here. Okay, let me again write the code that is build. So if I write a code build over here, and I'll explain it briefly. So if you see, oops, let me again paste it back. Okay, now if you see this over here, so what I'm trying to tell you, we have a function. It takes a vertex. Suppose we have some edge v. So what it does is it sees if v is in nodes. If it is in nodes already, so what it does, so if it is not in nodes, so then it performs. If it is in nodes, so it will do nothing. It will skip that node. So if v is not in nodes, so if it checks a whole of this. Suppose we have a graph. In that we take a node, and we want to see do we have to add it in nodes or not. So what we'll first do is we'll check if it is in nodes already. If it is not, then the first thing we'll do is we'll add to it. Okay, then we that we have children also. So what we do, we have this with this previous also. So with this previous should be set somewhere in the value object itself. Okay, so this v should have a previous value. Give me a second to set that. So instead of this previous, let's use children. So we have this over here. Okay, so because we don't have previous, so in the original code I have written previous, so in this I have written children. So what I'm trying to do is now for child in children, so you know that this children again is a set, so it will go for this v of children, it will take each of these and add those into edges. So it will take both of these and it will add those into edges, and it will again call recursively this build. So if you again see this, so you have a graph. Suppose I'll give you an example. You have a graph of this sort, a b, it gives rise to ab, suppose something of this sort, and we have then plus c. This is multiplication, and then we're adding c to it, to this ab. So we are getting ab, and then we are adding c to it. So this is add, and we have c, and now at total we have a plus b plus c. Suppose you give it a node or a graph. So let me take a, so you have this b, and suppose you have this c, suppose you have d of this sort, you have e. I'll just make some random graph now. So if you give it some vertex, and you know this c has these two are the children of this. So now when I'm trying to build this, when I'm trying to come up with nodes, and first I'm making a list of, I'm making a set rather. So if you see in this code, so the code over here shows nodes and sets as empty first, and then I'm trying to build this. So I'm giving the this vertex, so that's why you see build of v. Let's suppose at c point now. So if I'm giving c, I'll check if c is in nodes. If it is not in nodes, then I'll add this. So I'll add this c into the nodes. And then because I have to see edges correspond, the edges are a and c and b and c. These are the edges that I want. So that's what I'm saying. For children in v comma this, child comma v, because anyway I'll have to consider, I'll have to have a comma c as edge and b comma c as edge. These two should be my edges. So that's what I'm doing over here. So node, I'm adding this node. Suppose this case is c, and then I have to add edges ac and bc. So that I'm adding over here. So edges is this. So I'm again writing a for loop because I have the set of children with me. So this c has children a and b. So I'm iterating over a and b, and then I'm adding those into edges. So you see the child comma v. So initially I'll have child, that is a. So I'll have b, rather this will be initially a comma c. Yeah, this was right, and b comma c. So I'll have in children I have a and b. So I'll have children, child comma v, that is a comma v. V node in this case is c, and the second iteration will be b comma c. I hope this is clear. Is this clear, this build function? And again I'll recursively call the same thing on children, and then I'll start with a. I'll again do the same thing for the a. Okay, I'll keep on building this graph. I'll keep on building the edges and these nodes. Any questions on this? Now once we wrote this build function, now we'll use this build function somewhere. So we are basically inside the function. So if you see this trace, actually we were this inside this, we again defined one more function, that was this, and now we have to build from root. So we'll call this build function from root. So the root that we got. Okay, this is where we will build it from. Okay, and then if let's say there are not nodes, we'll raise an error, and then we'll return a graph trace. So in this we'll at the end, so I will just paste these lines for checking, error checking. So what I'm saying is, So I am saying over here, if not nodes, so if I am getting nothing, so I am saying empty graph, no nodes were found from the root. And then second thing, I am returning it graph trace, I am giving it to this nodes and edges. So this is what I am doing at the end. Okay, so if I have to do it on the graph, on some graph, suppose, and do we have graph here? Okay, we do have. So we do have this. So if I can create a trace, so before that, should I draw? Basically, let me do one thing. So I'll say trace of root. So what is the root we have? So we have root f over here. So trace of f. So if I see, say trace of f, and if you see, this is the graph trace. We have nodes. So in that nodes we have node label C, and everything is over here. If you see, so we have got nodes. These are my nodes, and we have got edges as well. If you see edges is A, comma F. This is one edge. Okay, and we have a lot of edges are there. We have the whole graph in which we have whole edge and we have all of this. So this is what it's doing. I'm just applying trace on this F. So this is giving me nodes and F, and you can again sketch it by hand. So if I have to write it hand, you can write that, but you can also check it over here with this. But I want to visualize this now, so I can now use graph trace. So in that we have a function which is called as digraph, as I said. So what I'll do is I'll have a function dot draw dot. So if I have to draw something, so I'll draw the function, because now I have nodes and these edges with me. So I'll say give me the root, okay, and I'll give you the digraph. Digraph basically means in that graph is we already have that defined. So what we can do is we can say from left to right draw this graph. So this is the syntax of graph is. So I'm saying dot digraph, and this digraph was imported from that graph is. I'm saying format is SVG, and we can have without SVG format even. And then I'm saying graph attribute is this. So this is all the standard documentation that you can check over there. And then I'll look for nodes and edges. I'll say nodes comma edges. Okay. This is nodes and this is edges. I'm taking it from trace of root. So because I'm taking the trace and I'm getting nodes and edges from this. And now I'll plot the graph. So what I'll do is, so I'll do this. So I'll iterate through all the nodes and I'll add them to, I'll add a loop. So I'll write a loop and then I'll explain the loop. If you see, for n in nodes, so I'm taking from each nodes, I'm giving it a special ID, a unique ID for these memory addresses. Okay, because I don't want to overwrite it. So then label is this. So this is n.label, and this is the data we have, and n.grad is also there. We are printing three things. I'm printing label, I'm printing data, and the gradient of that. Okay, then I'm using this dot node, because this is the digraphs standard documentation that you can see. I'm saying name is this UID, label is label string, and shape is in a record shape, and style is filled, and fill color with light blue. I'm also giving it some color. And then I also doing for the node, we also have operation. So if operation is given for that node, if it is not the node which is just at the end, or if it's just at the start, so I'm giving the operation, and I'm just creating a fake node. So this is a fake node. So why is this fake node there? Because I wanted to create something of this sort. So I want to create, if we have A, so I will create A, and then I'll create B. So then I'll create one more fake node plus, and then this will give me something. So that's why this code is for. If there is an operation, create a fake node. Okay, this node won't be used for computation anywhere, but this A and B will be used. Okay, so I just want to clarify this. Why am I doing it here? So if n or op is equal to this, and then what we can do is we can again run one mode, and for child and parent in the edges, we'll connect these two things, because we have this. We're drawing these lines now, and we'll have to connect these. So this iteration, this loop that you saw over here, this loop, so it will take nodes and it will draw these nodes, and now you have to connect these nodes. So what I'm doing now is for children and parent in edges, so I'm taking these edges and I'm connecting this. Take this UID of the child, and this is UID of the parent. Okay, I'm converting that, and then I'm saying dot edge. So here, if you see, I have written dot node. So I'm creating a node, and here I am creating node as well as edge. Okay, so here in this case, I am creating with child and parent in the edges, because that is a set, and then I am taking this UID of parent and dot edge, and now I can return this dot. So return dot will give me that graph. So if you want to understand it more, you just look at the graph is. Okay, so this is that. So this will give me the computational graph, hopefully. Okay, I'll have to visualize this. And now let's suppose if I draw dot of f. So I am draw dot of f. There is some issue because we have not given this because I told you I'm diverting a lot from, oops, we have defined OP, not this dash OP. Is there something else? Okay, can you see this? This A and B, we have data 2 and we have data this, and then the gradient is 0 by default, and then we are multiplying this A and B, and we are getting C out of this, we are getting D out of this, and this D is this, and we are getting C, and this is added, and this is the computation graph. How many of you can see this? So again, showing you this. So what we did is we tried to visualize this. So this draw dot is that I'm taking the root node. So again, showing it this. So it is taking this root. Okay, it is first coming up with trace, and in trace we are using that build function, and it is trying to build these nodes and edges. And then with this nodes and edges, what I'm trying to do, I'm trying to get a unique ID. So this is the unique ID I can get, and I'm getting the label. That is label, data, and grad. That's what you see over here. If you see a node in this, it has label, data, and the gradient. So that's what I'm printing over here. This is the label of that, and I'm saying dot node, give it a name of this because I want to keep it in the memory location, and if I want to connect these two edges together, then I'm giving it a label. I'm saying it that shape is like it should be a record, and style is fill. This is the standard documentation of graph. And now if it is an operation, if it contains an operation, okay, if it is a node which was a result of some operation, so I'm taking that and having this one more node. So if you see node in this, I have written shape ellipse, and it is filled, and it is filled with light this color. Because this is the color. Here it was light blue and some other color was given to it, okay, in order to say that this is a fake node. Okay, and then we have to connect the edge. So how to connect the edge? Because I have this operations node over here, and then this UID. So if you see this node, actually I want to come up with the ID, its unique ID. I said UID was the ID of the node, and I said end dot operation. Okay, I did something to come up with this ID. So I took this ID and the ID of the node. So that's why it's connecting over here. So if you see, this is getting connected. Okay, that's how the edge is being drawn. And similarly, if this goes on for a loop, and then we are taking child and parent from the edges and giving child a unique ID, parent a unique ID. So we are coming up with this parent ID, and then we're again connecting these together. So you see this unique IDs, we are using these unique IDs to come up with these edges, and this is one of the graph. Okay, and you can again say weight plus bias, this W of X plus B. So you can come up with this graph. And what we'll do is, so this A, B, C, and D, E, and F, so these things has gradients, because this, if you see this fake node, it doesn't have gradient, so we'll have to set these gradients, the computation graph that you see over here. And now we'll initially do manually. So once I fill the gradients, so I'll do the manual computation. Everything will be filled gradient. Let's suppose, how can I do this? So I can say F dot, okay, let me draw F, cut it over here, draw it over here, okay, so that it is not part. And then if I say F dot grad is equal to 1, so we'll compute manually everything, and then we'll say this is gradient. So if I set the gradient over here, and then if you see, this is not changed yet. So if I again run it, now you can see the gradient will be set over here. So grade is equal to 1.0. So what I'll do is, I'll take the whole of this computation graph. So I'll compute gradients by hand, and I'll first do this numerical gradient that we have done in many cases. We'll do manual back propagation one by one. And after that, we'll do the autograd. We'll have one more method that will apply over here. So that I'll just name, we'll say to do. So in this we'll define definition backwards. Suppose backwards. Okay, so once we call this, so I'll just write pass over here, or maybe this is my to do. Okay, what I'll do is, so in the next class, the first thing we'll do is we'll do manual back propagation. So whatever we have studied, we'll use those concepts to initialize all of these gradients. We'll compute gradients by hand, and then we'll initialize these by hand. And once we are done with that, so we'll write automatic differentiation. So we'll just apply F dot grad. So in this case, you saw we said F dot grad is equal to 1.0. We'll write F dot backwards. So that will perform the auto gradient on the whole graph. And once we are done with that, we are done with networks. Then we just have to come with a layer of neurons, or else, and then a network, and then we can train something with the bare bone basics. And I'll show you the whole network with this. So here I'll stop the recording. I'll take your questions.